Okay, we're going to go on to the next paper, which is, this time it's the June series, so it's June 2007, and again it's a foundation completion paper. It's either MF or M5, and it's non-calculator. So if you could have a look at question 1, and if you can answer that, we'll go through it in a few seconds. Okay, so we're choosing from there's 7 names to choose from, and hopefully you can identify that that's a cuboid shape. That's a cuboid. This one here is a pyramid shape. The faces all meet in a point at the top here, and this shape here is a cylinder. Okay, so have a look at question 2. We'll go through it in a few seconds. Okay, for question 2, the question's saying, Mary leaves home for work at 07:30, returns home at 15:20. How long is Mary away from home? Probably the best way to do this one is to break it down into different little blocks of time. So from 07:30 to the next hour, which is 0800, is 30 minutes. Then we can count on in the hours from 0800, that's 8 in the morning, through to 1500 hours, or 3 p.m. in the afternoon. We can count that it's 7 hours, and then we've got to get from 1500 or 3 p.m. to 1520, which is another 20 minutes. So when you add those two together, 30 minutes and 20 make 50 minutes. And then 7 hours, so the answer is 7 hours, 50 minutes. Okay, the next part B, tells us that Mary travels 10 miles to work, and she takes half an hour to get to work, and we have to find out what her average speed in miles per hour is. Best way to think of this is that in half an hour she travels 10 miles. So how far would she travel in 1 hour? So hopefully everyone can see that it's going to be double that. Half an hour is 10, so 1 hour is going to be 2 times 10, or double 10, which is 20 miles. So that means it's 20 miles in 1 hour, and that's exactly the same as 20 miles per hour. So the answer is 20 mph. This third section is how many kilometers does Mary travel to work? So remember, these are all linked, so you need to go back. Mary travels 10 miles to work, so you're going to have to change 10 miles into kilometers. Right, what you need to remember here is that 5 miles is equal to 8 kilometers. Now you have to learn that off, or either that or you learn off that 1 mile is 1.6 kilometers. So either way we can get our answer. So if we know 5 miles is 8 kilometers, then 10 miles, which is what we have to find, is going to be double 8. 8 multiplied by 2, because 10 is 2 times 5. So the answer then is going to be 16 kilometers. Or if you know this fact here, 1 mile is 1.6 kilometers, then 10 miles is going to be 10 times 1.6, which again gives you the same answer, 16 kilometers. Okay, so have a look at question 3. You can stop the video and have a go at it. We'll go through it in a few seconds. Okay, question 3a, and we're asked to calculate. So remember, this is a non-calculator paper, so we have to be able to do these just by hand. So we have to remember here there's an order of carrying out these different operations. You have to remember BODMAS. That tells you brackets is first, and then we do powers, then divide and multiply before add and subtract. So here we've got a divide sign, so we've got to do the divide first. So it's going to be 6 divided by 2, gives us the answer 3. And now we can go back and add that answer to the 14. So it's 14 plus 3 is 17. And the second one down here, this time we've got a bracket in this calculation. So remember, B for bracket, we have to do that first. So we have to work out what's in the bracket. 3 plus 5 is 8. Now we can go back and do the next operation, which we have to do the multiply before we do the subtract. So it's going to be 2 multiplied by what was in the bracket is 8. 2 multiplied by 8 gives us 16. And then we're going to take away the 4. So the answer is 16. Take 4 is 12. Okay, question 4. It's a conversion graph, and if you'd like to have a look at that, the second part says we're going to use the graph to convert 8 meters per second into kilometers per hour. Okay, so it tells us we're going to plot the conversion graph, and we're given a table with different values of kilometers per hour and meters per second. So we're going to plot this set of points, 0, 0. So put an X at 0, 0. The next set of points is 20 and 5.6. So we're going to go to 20 on the kilometers per hour, and then up to 5.6. Put an X there. The next set of points is 40, 11.1. So we go to 40 on the kilometers per hour and up to 11.1. And then 60, 16.7, and hopefully you can see those are a straight line. So I've drawn a nice straight line through all the points. And then part B says use your graph to convert 8 meters per second into kilometers per hour. So hopefully you know then we're going to go to the meters per second axis, which is the vertical axis, go along to 8. And you can use a ruler to draw a line over to your conversion graph and then down to the horizontal axis to read off kilometers per hour. Okay, hopefully you can see from 20 to 30 there's 10 little divisions, so each division is 1, so that means that's 29. So the answer is 29 kilometers per hour. Okay, so this is the same question, but it's part C, and if you have a look at that, we'll go through it in a few seconds. Okay, so part C tells us the speed limit is 45 kilometers per hour, and a motorcyclist is traveling at 12 meters per second. Is the motorcyclist exceeding the speed limit? So I hope you can understand that we're going to have to change one of these, say the 12 meters per second into, this is question 4, part C. So it tells us the speed limit in a town is 45 kilometers per hour, and a motorcyclist is traveling at 12 meters per second. Is the motorcyclist exceeding the speed limit? Right, so we can either change 45 kilometers per hour using the graph. We can change that into meters per second. So as you can see, we can go to 45 on the kilometers per hour axis and draw our line up to the graph and then horizontally across to here, and we can read off that 45 kilometers per hour converts or changes into 12.5 meters per second. So there we have it, 45 kilometers per hour is about 12.5 meters per second, and the cyclist is only traveling at 12 meters per second, so he's underneath the speed limit, so the answer is no. Or there's another way of doing it. Hopefully you can see you could change 12 meters per second into kilometers per hour, and again using the graph, 12 meters per second is about 43 kilometers per hour. And again, that's underneath the speed limit, so the answer is no. Okay, here's question 5a. You have a look at that, and we'll go through it. Okay, so 5a says, shade in one square so that the shaded shape has exactly one line of symmetry. Right, there's two possible answers here. If you shade in this square here, then there will be a horizontal line of symmetry. So hopefully you could imagine a line horizontally through there would be a line of symmetry if we shade in that square. Or the alternative answer is this square here. If we shade that square in, then there'd be a vertical line of symmetry. A line going straight up the middle there would be a line of symmetry. Okay, have a look at question 5b, and we'll go through it in a few seconds. Okay, 5b is asking you to shade one square so that the shaded shape has rotational symmetry of order 2. And what you're looking for here is a shape that rotational symmetry means it fits on top of itself when it makes a complete 360-degree turn, and it fits on top of itself twice. So the shape of the square that we need to shade in is this one, and if you want to, you can get tracing paper, and if you want to check, there's our shape now with this square shaded in. So I put a little dot there, and we're going to see where that dot moves when we hold the tracing paper in the center of the shape, and we're going to rotate it around a complete 360-degree turn. So there, the shape fits on top of itself once, and it's gone halfway around. Now to continue rotating the tracing paper, the shape fits on top of itself again, and it's made a complete 360-degree turn. So that's rotational symmetry of order 2. Okay, question 5c. If you want to have a look at that one, and we'll go through it. Okay, this is 5c. We're asked what the scale factor of enlargement of shape A going to shape B. So hopefully you can see shape A is getting bigger when it goes to shape B. So we're looking for the scale factor, which tells you how many times bigger each side is, or each the shape is. So we're looking to see how many times bigger is this side compared to this side of the shapes, or this side compared to this side. So hopefully you can see that each of the sides on shape B is 2 times bigger than the corresponding side on shape A. So the scale factor is 2. Okay, so have a look at question 6a. We'll go through it in a few seconds. Okay, so 6a, we've got a table of information about 4 workers at a store. They earn £7 per hour from Monday to Friday, £8 per hour on a Saturday, and we're interested in what Claire is earning. So the easiest thing to do here is, I think, is to circle all the times Claire's name appears, and then we're going to look and see how many hours she's worked. So this is Monday. She worked from 9 a.m. to 1 p.m. is 4 hours. Tuesday, Claire worked 5 p.m. to 9, which is another 4. Thursday, she worked 1 p.m. to 5, which is 4. Friday, another 4. And Saturday, another 4. So hopefully you can see that on the Monday to Friday, she worked 4 times 4, which is 16 hours at £7 per hour. And then on the £8 an hour on the Saturday, so she has 4 hours at £8 per hour. So that's 32. And when we add those together, we get £144.